Okay, now we're talking about centripetal acceleration. Centripetal means center seeking. Now, first of all, we have to briefly discuss uniform circular motion. Uniform circular motion, there's two conditions that must be met. Number one, constant speed. Number two, must be a circular path. And things that are turning corners, at least for a brief period of time, will act that way. So when we look at a discus thrower getting ready to spin, she's spinning at a somewhat constant speed, and of course the discus travels in a circle. Now, is an object that's undergoing uniform circular motion accelerating? And this is kind of the crux of the problem. Velocity and a change in velocity is our definition of acceleration. And so therefore, if you're changing velocities, you are accelerating. Well, remember, velocity is speed in a particular direction. If you're changing directions, you are accelerating, and therefore it requires an unbalanced force. So now let's take a look at the direction of centripetal acceleration. So we're having an overhead view of something moving around the outside of the blue circle. So my initial velocity is always going to be tangent to the circle. Remember, if I don't have that force pulling it inwards, it's going to go tangent to the circle. That's Newton's first law. So the second point is that's my final velocity. I'm going to look at that little segment in which the thing moved about a sixth of the way around the circle. Well, we know that change in velocity is acceleration, and that's equal to Vf minus Vi. Well, I'm going to rewrite Vf minus Vi as Vf plus a negative Vi. I haven't changed anything, but I need to add vectors, so it's important to do it. First of all, I want to draw Vf. Then I'm going to add Vi to it, tip to tail, but in the opposite direction of the way Vi is. So that's my Vf. Vi acts straight down, so therefore the acceleration is from my starting point to my finish point. Notice how that's approximately directed towards the center of the circle, and that was just freehand drawn. So therefore that should verify that the acceleration is actually towards the center of the circle. Now, key thing to understand, the velocity is always going to be tangent to the circle, and the acceleration is always going to be towards the center of the circle. Matter of fact, anytime you have velocity and acceleration perpendicular to each other, you're going to have something moving in a circle, or at least a part of a circle. That happens. Now, the magnitude of acceleration is found by the formula v squared over r, and that's the centripetal acceleration formula. There's a derivation of it. If you want to look it up, you can. Now, let's check the units, because remember, units are our friends. Well, velocity squared would be meters squared over seconds squared divided by radius. Radius is going to be in meters. Simplify that, I get meters per second squared. Yay, that's an acceleration. Much rejoicing. Yay. Now, if an object is accelerating, is the speed always increasing? No. It can happen when I'm turning a corner. Well, I can turn a corner and keep my speedometer on the same value and not have it change, the speedometer change, but I'm still accelerating. There's an unbalanced force. So when I round a corner, it can happen. If I look at the skier here, as he water skis, the centripetal acceleration is going to be straight up the tow rope. That's where he gets it from. So that's a centripetal acceleration. But his body is trying to go perpendicular to that, out at that angle. So there's a right angle between those two. Now it's three-dimensional, so it's a little bit harder to see that there's a right angle to it. But his body wants to go tangent to the circle. It's the centripetal acceleration that causes him to go inside. If you have a centripetal acceleration, you also have a centripetal force. Now, an automobile moves at a constant speed down one hill and up another hill. Which of the following best represents the directions of velocity and acceleration of the automobile at the instant it is shown? Well, we know that velocity is tangent to the circle, so it's going to be going off to the right. So that eliminates a couple choices. We also know that acceleration is towards the center of the circle, so therefore it looks like that. So therefore the winner is B. A person of mass 60 kilograms is located at the top of a Ferris wheel as shown. The wheel spins at 6 meters per second, has a radius of 4 meters. What is the direction of her centripetal acceleration? Well, she's sitting there. She's being pulled towards the center of that circle. So therefore it's towards the center. Now let's calculate the magnitude of her centripetal acceleration. So in other words, now we're trying to get a numeric answer. A is equal to v squared over r. So it's 6 meters per second squared divided by 4 meters. 6 squared is 36. 36 divided by 4 is 9 meters per second squared. Now, what is the shape of the graph below? I want to graph centripetal acceleration versus speed. Well, remember, our equations are guides. And this equation tells you that AC is equal to v squared over r. Now, they didn't mention r, so therefore I don't have to put anything on it. I really want to look at just how AC and v vary. Well, looking at my graph, AC is on the y-axis, v is on the x-axis. But what it says is y varies with x squared. Y is proportional to x squared. The little fish sign means proportional. So therefore, y varies with x squared. Well, that's a parabola. So therefore, it looks like that. Centripetal acceleration is more dependent on speed than anything else. Hope this helped.